In this video, we're going to be looking at lesson 9, which is page 26 of your booklets. If you've already had a good shot at lesson 8, so that's basically using calculus to help us optimize, then please start this now. If you haven't quite finished off lesson 8, I'd recommend going back, doing a few more questions, then doing lesson 9. Reason being is these are trickier, and it's probably better getting a better base first before you come into this. So there's sort of more extension work, these questions. So let's get cracking. First question, a rectangular box has a square base of length x. Its framework of 12 edges is constructed from pieces of wire of total length of 36 centimeters. Determine the height of the box in terms of x. So what I'd do here is probably want to start off by drawing this shape. So we've got some kind of rectangular box, and it says it has a square base, so we can dash all those. And we can see here it does have 12 edges, 4 on the bottom, 4 on the top, and 4 on the side. So it looks like we've done a good thing. And all of those lines there, they're indicative of those wires. So we know that in total the length is 36 centimeters of wire used. Determine the height of the box in terms of x. So I think they're wanting us to get an equation first for the length of y and then rearranging, so to make h the subject. First thing is what I'd do is you've got your h's here, so assume, and these are all the same. That's the height of the rectangular, square base, a rectangular box. And let's find a rule. So we've got 36 centimeters of wire was used. There's 4 h's and there's 8 x's because they've said that these are going to be x. And so there's 4 in the bottom square and 4 in the top square. Now let's make h the subject by rearranging. We can see 4h is equal to, and then we've got 36 minus 8x, and then we can go 9 minus 2x by dividing all by 4. And this is our formula for the height in terms of x, and that's centimeters. The next one's to show that. So they've given you the answer here. You just need to show that that's the answer. Show that the volume of the box is equal to this. Now, you don't have to worry too much about this. Just go straight to what's the volume of this box and then rearrange it, manipulate it until it looks like this here. So here we go. The volume of this box is going to be base, which is x squared, times by height. Now we can see here that there's no h's in that equation. So what do we want to do? We want to swap out that h. This part here is an indication of how to do that. Where we see an h, we're going to replace it with 9 take 2x. Now this looks like it's an expanded form as well, so let's expand. And you can see that we've shown it. So we've got a square there to say that we've shown it. There we go, we've done that. Determine the value of x for which the volume of the box is a maximum. So they're wanting you to use calculus here, maximize, so we want to differentiate and solve equal to 0. Also state the height and the maximum volume. So let's have a crack at this. dv by dx is going to be 18x take 6x squared. Make it equal 0 to find those stationary points. Factorize out. And then we can see we've got 2 points. X is either equal to 0 or 3. Now we know that 0 probably doesn't make much sense. And if we have a look at this graph, we know it's going to be a negative cubic like that. So we're expecting x is 0 here and this one's 3 here. So we know we found the maximum. So we found the value of x. So we can say x is equal to 3 centimeters. They haven't asked us to confirm the nature of that point. There we'd have to use the double div test to test that one, but we don't have to because it doesn't ask us to. So we found that. State the height and the maximum volume. Okay, so height, we can use this rule here, 9 take 2x. So here we go, height, 9 take 2x. So therefore it's going to be 3, because it's 9 take 6 is 3 centimeters. Okay, so the height's 3 centimeters. And what's going to be the volume of this at a maximum? Well, we've got x squared times h, sub in 3 squared times 3, 27 centimeters cubed. So now we can say the box has a maximum volume of 27 centimeters with dimensions of 3 by 3 by 3. Now remember that rule of thumb. If we want to maximize, typically for rectangular prisms, it will typically tend towards a cube. That typically maximizes the volume. If you start stretching it out, the volume decreases. So that there is usually the best for a rectangular shape. Same with the square. If it's a 2D shape, you'll tend towards that. Okay, so hopefully you went okay on that one there. We're going to move on and have a look at the next question. Okay, which is example 19. Okay, at the end of example 19, I'm going to pause the video and make a new one. And if you've had a shot at example 20, it's a little bit crazy, so we're going to fix that up a bit. So here goes example 19, and I'd recommend, if you feel confident, have a shot and then watch this video. So rectangular boxes that are to be made, each box is to have a square base of sides x and a height of y. So this is very similar, but this is actually a box rather than a wire like framework. The base and top are to be covered with lacquer, costing $5 per centimeter squared. So they're coating it. And the sides with lacquer costing 4 centimeters squared. Find the values of x and y, which minimizes the production cost if the volume of the box is 80 centimeters cubed. Now we've got to minimize this time, which is, usually we're trying to maximize things, but minimizing cost also makes sense. First thing I'd recommend doing is starting off with some kind of rectangular prism shape, just to get our ideas here. It's saying make the sides be x. Oh, wow, how to do that? Let's get rid of that. I was going to choose that one there. Okay, and it's also saying the height's going to be y, so let's do that too. There we go, and these are all the same here as well. All right, so we've got that there. We've made a diagram. Now let's consider our situation. It's saying that the volume of this, so volume is going to be x squared y, is going to be 80. Okay, so that's one equation we've developed there. And it seems like you want to minimize the total cost. So let's have a think about what this cost equation could be. So cost equation, it says that they're covering the base and the top with lacquer that's $5 per square centimeter. So we know that the area of the top and the bottom is going to be in total 2x squared. And then we're going to times that by the cost. So every unit, it's going to cost $5. Right? So that there is going to be the total cost of lacquering the top and the bottom. The next part is the sides. Now we've got 4 sides there, and the area of each one of those is xy. So there, this is the area, and these sides are going to be $4, so a bit cheaper. So this is the tops, top, bottom, and this one's the sides. This here is the area of the side, and this is the dollar rate per the side. Okay, and the same for the other side there. Now we've got a cost equation. As always, we don't like to have x's and y's. We want to have only one variable. And we can see that, and let's call this equation 2. Equation 1 can help us swap out those y's for x's or x's for y's. It depends which way you prefer to do it. I'm going to swap out y's. So here we go. Let's rearrange that equation. Divide both sides by x squared. And now I've got equation 3. Now I can swap all my y's with my x's and the equation gets a bit better. So let's sub that in. Okay, so here we go. Cost is equal to, and I'm just going to expand this first, 10x squared plus 16xy. Then I'm going to sub in. Now I've written this as x to the negative 2 because we know that x to the squared is equal to 1 on x to the squared is x to the negative 2. So I'm just bringing that up. Let's keep going. Now 80 times 16 is 1280, x to the negative 1. Okay. So what we've got now is we've got our cost equation just in terms of x, and we can call that equation 5 if you want, just it's a cleaned up version. Now what do we want to do? Well, we want to minimize this. So let's differentiate dc in terms of dx. Don't forget that negative 1, very easy to forget that. To minimize, now to solve these kinds of quadratics, we don't really like these x to the negative 2s or any negative powers, so we can do a little trick where we times them all to make them all positive. So what we do to one term, do to everything, we're going to times them all by x squareds. Now, we know here that x to the negative 2 times x squared is x to 0, right? So they cancel out. So you're just left with a number there, 1280. Let's solve. This is just a normal solve because only one x variable. Okay, now 1280 divided by 20, it's actually really nice. Divide by 2, then divide by 10, you'll find it'll be 64. And let's take the cube root, 4 centimeters. Now there's no plus or minus answers here, it's just simply 4 centimeters. Now what we've found is we found a stationary point, i.e. the gradient was 0. How do we know if it's a positive or a negative? Okay, well we can do our check. So I'm going to use my double div test just to make sure that we indeed have a minimum here. So let's differentiate once more. And sub in 4. And we can see here that, let's just double check this. We get an answer of 60. Now, if the double div is positive, we can say that this point is a minimum. So we've just confirmed it using the double div test. So what have we done so far? We've optimized, we found x is 4 as an optimal solution, and then they typically ask for, can you find the values of x, y as in the height, and also the minimum cost. So let's sub it all in now. So here's our summary. We've got x is equal to 4. So what's going to be our y? We sub into our equation up, where is it? Equation 3, 80 on x squared is equal to y. So y is going to be equal to 5 centimeters. And then the volume, sorry, not the volume, the cost. Let's find out that cost. So we want to sub in that into our original formula. So we can use equation 5, for instance, or even equation 4. Let's use equation 4. So let's find out that cost. $480. So that's our minimum cost there. And there we go, we've answered that question there. Definitely a bit trickier. Why these are called extension questions is because we've got those negative powers, and it just makes it it just makes it more tricky basically. There's more things to think about. And also the situation here, you have to really consider lacquering top, bottom, and making up cost function. Okay, so hopefully you found that useful. In the next video, we're going to be looking at examples 20 and 21. Thank you.